Guys, in this video, we're going to be talking about nuclear stability and transmutations. So in this video, we should be able to, at the end of it, predict nuclear stability and the type of decay that's going to occur based on the stability and the proton-to-proton ratio of an isotope. We're going to be able to write our nuclear equations for transmutation reactions. We'll be able to calculate the age of objects using carbon dating. And do half-life problems, and we should be able to list some radiation units and recall some of the devices used to measure radiation. So when we talk about nuclear stability, we're talking about the stability of a nuclei. And this stability is going to be based on the size along with the proton to neutron ratio. So what we see over here on the right is a graph with our proton and neutron ratios. And the little black dots we see, we call that the belt of stability. So any one of the nuclei, those with a specific neutron to proton ratio, are going to be considered stable. So they're not going to radioactively decay. But those that are not, the ones that are in orange, are going to be unstable. And the stability is based on, again, the size and the neutron to proton ratio. So if we look at the neutron to proton ratio, we can determine what type of decay we would expect based on what type of instability exists within the nuclei. And as a point of reference, there's also a 1-to-1 neutron to proton ratio line. That's the red line in there. And that's just showing how much deviation we have from that 1-to-1 neutron to proton ratio, especially as we get higher and higher in mass. So if we are on one of those black dots, we're good. There's an ideal neutron to proton ratio, and it's a stable nucleus. If we are above that point, so anywhere in this region, anything above there, and let's do it as a color instead. Anything above that is going to decay via beta emission. Okay, so what happens if we are above that neutron to proton ratio? We have too many neutrons, and that means we're going to decay one of those neutrons to produce a proton. So we'll have a neutron convert into a proton, and during that process, there'll be emission of a beta particle. If we have a nuclei that exists below this ratio, then we have too many protons. Too many protons, we're going to convert one of those protons into a neutron. So we're going to do positron emission or electron capture. In both of those cases, you're going to convert a proton into a neutron. In the case of an electron capture, you're going to capture an electron by a proton, and it'll combine to form a neutron. In positron emission, you're going to decay a proton into a neutron and a positron. Either way, you're going to convert and get one more neutron, one fewer proton. And then if we have something that is just too large, so up here, this is our Z number of 84 and greater. It's too large, so it's going to go ahead and decay by It's going to go ahead and decay by alpha emission. And that'll allow it to lose 4 mass units in just one decay. Okay? Just to summarize, if we are above, there are too many neutrons. So we're going to decay by beta emission. And in that process, a neutron converts into a proton and an electron. If we are below, there are too many protons. So we're going to have either electron capture to produce a neutron, or positron emission to produce a neutron. Either one. And then if we are above a Z number of 83, so Z is greater than or equal to 84, it's going to be alpha emission because it's just too big. So we'll have the discharge of an alpha particle, such as what we see with uranium. It will decay via helium nuclei or our alpha particle to give us thorium. Okay? So by doing this, we can stabilize our nucleus by losing our beta particles or positrons or gaining electrons or alpha particles. All of those things are in order to get to a stable nucleus. And I'm just going to real quick go over some generally stable nuclei. So we got what's called magic numbers. And these are numbers of protons or neutrons that are considered highly stable nuclides. So for our protons, if we have numbers of 2, 8, 20, 28, 50, or 82, these are more stable nuclides. And then for neutrons, it's going to be 2, 8, 20, 28, 50, 82, or 126 neutrons. Either one will lead to more stable nuclei. Also, if we have even numbers of protons and neutrons, we're going to have a more stable nuclide. If we look, 157 of our stable isotopes have even number of protons and an even number of neutrons, and then any one of them that have odd are much less likely to be stable. So even numbers of nucleons equal stable, or more stable at least. And then, as I was talking about on the last slide when we were talking about nuclear stability, we go through nuclear transmutation reactions in order to get to a stable nucleus. But sometimes going through one transmutation is not enough. And we can see this if we look at the uranium decay process. So uranium will go through several decays before it will get to a stable nucleus. So it's not necessary that only one stabilization can occur after one nuclear transformation. So stabilization may require multiple transformations or transmutations in order to become stable, or in order for a nucleus to become stable. Okay? So they could undergo a series of decays. Here are some of the particles that we're going to find in nuclear reactions, in those decay processes. You should be familiar with all the different types. So how we write a neutron, how we write a proton, how we write an electron, alpha particle, beta particle, and a positron. So you should be able to write each one of these, and they'll help when writing a nuclear equation. So writing those nuclear transmutations and balancing out the nuclear equations requires us to balance out the number of protons on both sides and the mass number on both sides. So to balance a nuclear equation, the mass numbers on both sides of the equation must be equivalent, or must sum to the same value. And so must the atomic numbers. So when we look at these particles, we see that they have a mass number on top and not always an atomic number on bottom. So for the neutron, the proton, the alpha particle, those are all the atomic numbers on the bottom. But for our beta particle, our beta particle, electron, and positron, there's a positive and negative, and it's just the charge, but it still will help us to balance out those atomic numbers if we keep those in mind. Okay, let's move on to half-life calculations. So determining the half-life of something. So a half-life, which we always write it as T1/2, describes the amount of time it takes for half of the sample to decay. And it's of a radioactive species. Is the time it takes for half of the substance to decay. And it's going to be an exponential decay, so it's going to look like this. Okay, so it's not going to be a linear relationship here, which is one of the reasons why nuclear waste is so hard to get rid of, because it doesn't just decay and become stable in a linear fashion. Okay, so as a note, the half-life is independent of amount of sample, temperature, or pressure. So you can't speed it up or slow it down just by changing a variable. And if we look over in this table right here, we see that our half-lives can vary pretty significantly, from fractions of a year to millions upon billions of years. Some of them are for fractions of a second, their half-lives. So they're going to vary wildly. And generally things that have really, really short half-lives, though they do not last very long, they're generally considered a little more dangerous because you're going to be exposed to a lot more radiation a lot more quickly. So our calculations for half-life, we have two that we're going to look at. First, we want to know number of half-lives. Which is given as n, and n is equal to time divided by the half-life. So if 2 years has gone by and the half-life is a year, 2 half-lives have gone by. And then we also have amount of substance left at a given time. That's going to be A times T is equal to A naught, which is our initial amount, times by 1/2 N. So that's that. And then this A naught is initial amount. Okay. We use the half-life of carbon in order to do something called carbon dating. And carbon dating is a technique that's used in order to find out the age of something that was once living. So by living, it had to have been something that it was taking in carbon in some way, either breathing it in like a plant would, well, not breathe, but absorbing it like a plant would, or eating something that contained carbon. So it has to in some way take in carbon. And as an organism is alive, it's going to take in carbon in the form of carbon-14. A little bit of it at least. So a living organism takes in carbon-14, which is radioactive. And as it takes it in, it's going to slowly decay to carbon-12, but it's going to continuously replenish that carbon-14 as it's living. However, once the organism dies, it no longer takes in carbon-14. So all of the carbon-14 that remains is going to slowly decay to carbon-12. Okay? And you can look at the ratio of carbon-12 to carbon-14 to determine the age of a substance. Okay? And what happens is you can compare that dead thing to something that is currently alive. So you can actually get the initial, like this is how much initial carbon-14 we have, so that would be our A naught. And then you can look at how much carbon-14 remains, that could be your A, and then from there you can figure out how many half-lives have gone by. And since the half-life of carbon-14 is known, you can determine how many half-lives had gone by. Okay, we're briefly going to look at the idea of measuring radioactivity. So what devices are used in order to measure radioactivity and units that are used in the measuring of radioactivity. So many devices exist to measure radiation. So the presence of radiation or radioactivity, what's actually going on. The basic requirement must be that it has to interact with radiation. As in the detector does. So the detector has to interact with radiation in some way. The most common is the Geiger counter. It's also called the GM, which is the Geiger Mueller meter. And it's the thing that like beeps as radioactive particles are hitting the detector. So it makes a sound as radioactive particles are hitting the detector, and it's also going to come up on this screen. Here are a couple of different units. We see over here the Curie, the CI, the Becquerel, the BQ. So two famous scientists within radiation, which makes sense as they're going to have units named after them. A fairly common radiation detector is a film badge. They use this a lot in areas where people are going to be in contact with radiation, and they use it just to see what kind of exposure people are getting. Radioactivity was first discovered by Henry Becquerel. Because it fogged up a photographic plate. And that's how they came up with the idea for a film badge. So this film itself is a photographic film. It's used to detect radiation, and the more exposure, the darker the spot. So photographic film is used. So this is a pretty simple way of measuring radioactivity. Um, and it's really for people who probably aren't getting a lot of exposure, but they want to make sure that the exposure is not getting too great and that they stop someone from getting too much so that they don't get sick. Photographic film is used, and as it is exposed to more radiation, the film gets darker and darker. Okay, let's talk about our Geiger counter again. Just kind of go into what's actually going on with the Geiger counter. It's also used to measure the amount of activity or radioactivity present in a radioactive sample. And while the film badge is something that's kind of long term, you're looking at exposure over a long period of time, the Geiger counter is something that's going to look at a lot of radioactivity at one time. So it's probably going to be exposed to a lot more radioactivity in a shorter window than the film badge will. So what happens is there is a window right here. So radiation will enter the window. And when it does, a gas is created. And when it does, it interacts with a gas, the argon gas within the chamber. And that argon gas is ionized. Okay. And then from that, an electric current is produced, and that electric current is what's actually measured. Okay. Next thing we want to look at is phosphors. Phosphors are a substance that emits light when absorbing radioactivity. So basically it excites the phosphor. That phosphor then, as it relaxes back down, is going to emit light. Okay, so the phosphor itself is going to emit light. The instrument that uses the phosphor is going to measure the amount of light to determine the amount of radioactivity. Okay, and this instrument is called a scintillation counter. And then once it measures that amount of light, it's going to convert that light into an electronic response. And that's the response that the instrument actually measures. Last thing I want to talk about is radio tracers. So we're going to switch gears just a little bit. A radio tracer is a radioisotope used to study a chemical reaction. Okay, here is a table of some radionuclides that are used as radio tracers. And generally what they're used for is within the medical field. And it's to look at a function of something. So you can actually use these radioisotopes to image specific areas within the body to see if things are working correctly. So for instance, if there's an issue with the thyroid, if there's some sort of thyroid issue, they can use iodine 131, which is taken up by the body just like regular iodine, but it can actually visualize the thyroid once it's absorbed by the body. So these are going to be used to diagnose issues within medicine. So it's going to follow along a chemical pathway. Being imaged. It's being imaged because it's emitting radiation. That radiation can be observed using phosphors. And this can allow for the diagnosis of many medical maladies. Right, like thyroidism. So, like I said, you're going to get the radioisotope. So the radioisotopes are administered to a patient. And then generally intravenously, and then followed. And like I said, it allows certain tissues to be observed. Or imaged. Okay, and that is everything